Hello students, I Dr. Dhirendra Kumar Shukla, Associate Professor in the Department of Engineering Mathematics at Technocrats Institute of Technology, Bhopal. Today we are going to discuss a topic of Engineering Mathematics Level 1, that is vector space. So, in previous lecture we discussed about the fundamentals of vectors. Now we will discuss about some properties and questions and theorems, etc. So, algebra of a vector space. So, theorem 1. The intersection of any two subspaces of a vector space is also a vector space. So, to prove this theorem, we can consider let W1 and W2 be two vector subspaces of VF, then clearly 0 belongs to W1 and 0 belongs to W2 because W1 and W2 are not empty set 0 belongs to W1 intersection W2. Thus, W1 intersection W2 not equal to null set or phi. Let alpha beta belongs to W1 intersection W2. This implies alpha beta belongs to W1 and alpha beta belongs to W2. Since AB belongs to F and alpha beta belongs to W, so we can write here A alpha plus B beta belongs to W since W is a vector subspace. And AB belongs to F and alpha beta belongs to W2. This implies A alpha plus B beta belongs to W2 since W2 is also a vector subspace. The same condition we can consider for W1 also. So now A alpha plus B beta belongs to W1 and A alpha plus B beta belongs to W2. So A alpha plus B beta belongs to W1 intersection W2. For all AB belongs to F and alpha beta belongs to W1 intersection W2, we can see here A alpha plus B beta belongs to W1 intersection W2. Hence W1 intersection W2 is a subspace of vector space over field F. Another theorem is the union of two vector subspaces is vector subspace if and only if one is contained in the other. The union of two vector subspaces is vector subspaces if and only if IFF is read out as if and only if. So W1 subset of W2 or W2 is subset of W1. So to prove this theorem, first we assume that W1 and W2 are two vector subspaces over field F and one is contained in the other, that is W1 subset of W2 or W2 subset of W1. Then W1 union W2 equals to W2 or W1. Since W1 and W2 are vector subspaces, then W1 union W2 is also a vector subspace. So converse, now we assume that W1 in union W2 is a vector subspace, then we prove that W1 is subset of W2 or W2 is subset of W1. Now to prove by contradiction, let us consider W1 is not a vector subspace of W2 and W2 is not a vector subspace of W1. So then W1 since W1 is not subset of W2, this implies alpha belongs to W1 but not belong to W2. W2 is not subset of W1, so beta belongs to W2 but not belongs to W1. Now alpha belongs to W1 and alpha belongs to W1 union W2, beta belongs to W1 and beta belongs to W1 union W2. Since W1 and W2 in case of union is a vector subspace, then alpha belongs to W1 union W2 and beta belongs to W1 union W2. It means alpha plus beta also belongs to W1 union W2. For this implies alpha plus beta belongs to W1 or alpha plus beta belongs to W2. Since alpha plus beta belongs to W1 and alpha belongs to W1, this implies alpha plus beta minus alpha belongs to W1. So beta belongs to W1, which is a contradiction. That is, our assumption is not correct. So that the union of two vector subspaces is a vector subspace if one is contained in the other. So the theorem is proved. Linear combination of vector space. Let VF be a vector space and let alpha 1, alpha 2, alpha 3 up to alpha n belongs to V, A1, A2, A3 up to An belongs to F. Then any vector is represented by alpha is equal to A1 dot alpha 1, A2 dot alpha 2, A3 dot alpha 3, An dot alpha n is called linear combination of vector space. Linear span of a vectors. Let S be a non-empty subset of vector space Vf, then the set of all linear combination of finite set of S is called linear span of S. It is denoted by Ls. The set S is called generator of Ls. So S is equal to alpha such that alpha 1, alpha 2, alpha 3 up to alpha n. Here Ls is equal to alpha 1 dot a1, a2 dot alpha 2, a3 dot alpha 3 up to an dot alpha n. So where all alpha 1, alpha 2 up to alpha n belongs to V and a1, a2, a3 up to an belongs to F. So we have a question here. Express 1, 7, minus 4 as a linear combination of vectors 1, minus 3, 2 and 2, minus 1, 1 in V3R. So how can we solve this question? Let alpha 1 is equal to 1 minus 3 2, alpha 2 is 2 minus 1 1 and V is equal to 1 7 minus 4. We seek scalars of A1, A2 belongs to R such that V is equal to A1 dot alpha 1 plus A2 dot alpha 2. So by considering and putting the values, we can get here 1 7 minus 4 is equal to A1 times 1 minus 3 2 plus A2 times 2 minus 1 1, and by making the distribution we can see the result in next line. Then making the comparison, we get three equations like a1 plus 2a2 equal to 1, minus 3a1 minus a2 equal to 7, 2a1 plus a2 equal to minus 4. And by making the solution by using normal mathematical process, we can get here minus a1 equal to 3, that is a1 equal to minus 3. Substituting the value of a1, we can get the value of a2, that is 2. And by putting the values, we can check here 2 minus times minus 3 plus 2 is equal to minus 6 plus 2 is equal to minus 4. So the equation is satisfied. So finally, we can get result here 1 7 minus 4 can be written as minus 3 times 1 minus 3 2 plus 2 times 2 minus 1 1. So this is the required solution of the question. Linearly dependent and linearly independent. Let S is equal to alpha such that alpha 1, alpha 2, alpha 3 up to alpha n be the set of vector spaces there exist A belongs to F, then A such that A1, A2, A3 up to An belongs to F such that A dot alpha 1, A dot alpha 2, A3 dot alpha 3 up to A dot n alpha n is equal to 0 is called linearly independent if all AI's are 0, that is A1 equal to 0, A2 equal to 0 up to An equal to 0, and called linearly dependent if all AI not equal to 0. Clear? So here we can see the question prove that the vectors x1 up to x1 equal to 1 0 0, x2 equal to 0 1 0, x3 equal to 0 0 1 are linearly independent. So x1 is equal to 1 0 0, x2 equal to 0 1 0 and x3 equal to 0 0 1. So again we consider three scalars a1 a2 a3 belongs to F. Then make the condition a1 dot x1, a2 dot x2, a3 dot x3 by putting the values here a1 times 1 0 0, a2 times 0 1 0, a3 times 0 0 1. The result is 0 0 0. So performing scalar multiplication and vector addition, we can get here a1 a2 a3 equal to 0 0 0. By comparing them a1 a2 a3 0. So all the results are 0. So the given vectors are linearly independent. Clear? So this is the simple clarification of the definition. So here again by discussing about the linearly dependency and independency, we can see this is the second part of the chapter vector space. Here we discuss about some important theorems and properties, and which is called algebra of vector space, and some questions related to dependency and independency. So by studying this lecture, this video, you can practice the questions given in your notebook or discussed in the class. So we will meet next time in next lecture. Thank you.